Hi, I'm Harold Schuch. I'm a lecturer in civil engineering at the University of Colorado, Denver. I am pleased to bring you this module about three-dimensional adjustment. This is module number 5, and it does require watching the previous modules. Otherwise, this will become hard to understand. So I suggest you do that first if you haven't done so yet. Now, a parcel of land is defined by a traverse. It's a figure made of sides, in this case 4 sides, and corners. The idea being is that if we make measurements of these sides and calculate coordinates of these corners, if we end up with errors that prevents us from closing this figure, then we will have a misclosure. If the misclosure is too large, then we will have to redo the measurements. If the misclosures are acceptable, depending on the project purpose, then we can do an adjustment, and that would help us calculating this set of data appropriately. Now, in each case, we're going to take into account for our adjustment the direction of each leg has a direction, the length of the leg, and the elevation of each corner. In this case, we have accepted certain things as given. We have accepted that the point A has certain coordinates, x, y, and z. So this point has this horizontal position locked in and this elevation locked in. That means that this point will not shift laterally and will not shift vertically up and down. There's something else we need to do, and that is that this figure can still rotate around point A freely unless we somehow fix that rotation. And we do that by taking some other point with known coordinates, and we determine that this point has a certain direction given by this bearing from point A. So this is the bearing, means that we have an angle that is from north. That means from this north direction, this angle here, and this angle goes towards the west. In other words, it swings left. It doesn't swing right from north. So this is what this bearing means. So to repeat, this bearing angle tells us that this line has a direction from A to P, which is inclined from north by a total of about 50 degrees towards the northwest. Now, we can convert this bearing into something that is much easier to calculate with, and that is called an azimuth. So we convert this bearing into this azimuth. What does this mean? This azimuth is always measured from north and expressed clockwise. So it's from north, and this angle here turns out to be about 309 degrees. So that's the azimuth from A to P. Now we add this arrow here because this shows us that this is the direction that is being expressed and not that direction. This opposite direction would actually be 180 degrees different. Now we set up an instrument on point A, which has these known coordinates, and we put a prism at point P, and we measure this line, and we obtain 3 types of information from the instrument, from a total station. We get the slope distance of the line from the instrument to the prism head. We get the horizontal direction as expressed in the instrument from here to here. Now keep in mind that the instrument does not know where north is. That means that this is an arbitrary direction that the instrument wakes up with when it is pointed towards point P. Then we turn the instrument towards point B and take the prism from P to B and make this measurement, the measurement of this traverse line. And here we obtain these 3 data sets. One is the slope distance, the horizontal circle direction of the instrument. Again, this is not related to north. And the vertical angle from A to B. So if we take this horizontal circle reading and we subtract this horizontal circle reading, we actually get this angle, which happens to be about 35 degrees. That's what's calculated here. So now we do have this angle, which is great because if we have this azimuth and we have this angle, we can calculate this azimuth. But the first thing we do is here we have measurements that were taken for this line. That means that we can now record these measurements in our field node table. And this is the table that is used for many things. One is to record measurements in the field. This table can also be used for calculations, as we will see, and this table can also be used for the purpose of delivering data to a customer. So those three purposes are very important in surveying. So what do we have here? We have several columns here. In the first column, we write down where do we place our instrument. Right now, we're standing with the instrument on point A. And at point A, we have this height of instrument, and our prism has this height of reflector. And from A, we're pointing towards B, and we have realized this horizontal circle reading, this vertical circle reading, this vertical angle, and our slope distance. We can use this information to calculate the horizontal distance with the help of this vertical angle and the slope distance to come up with this. And we can also calculate our vertical difference, the vertical distance. And there's a drawing I will still show that shows those magnitudes. So now that we have this azimuth as given, we have this angle calculated, we can now calculate this azimuth as it is shown here. So we have achieved two important things. This figure is held in place by this point. It's not shifting laterally. And this azimuth prevents this figure from rotating freely. So it is locked in place. And now we can continue collecting the data for the remainder. So what we will do is we will set up, while the instrument is still set up here at point A, and we have determined this azimuth, we can now take the prism from B over to D and measure this distance here. And we get these measurement data here. So a new slope distance, a new horizontal circle reading, and a new vertical angle. And we put this information and this information into our table. So here you have the shot from point A to point B with its data, and the shot from point A to point D with its data. So again, this is the horizontal circle reading, the vertical angle, and the slope distance. Now, obviously, if I now set up on point B and C and D and make those measurements that I can do from each point, then I can fill in my table, and it will look like this. This is the first of all, the information I collect in the field. I now move the instrument from A to B and measure this distance again by putting the prism here. Then I move the prism up here and measure this distance here. Now this is called a back sight, and this is a foresight. So these are my measurements that I took from point B. Then I move the instrument from B to C, take the prism to point B, and do a back sight from point C and get these measurement data. Then I shoot from C towards point D, where my prism is now, and I get these measurement data. Finally, I set up my instrument on point D and shoot backside information and foresight information towards A. So all these data I carefully record in my table. Now here I assume, for instance, that at point B I have a different height of instrument than at point A. That's actually normally the case, that you have different instrument heights every time you set up the instrument new. It's very possible that you don't change the length of the staff of your prism. Therefore, all your prism, your height of reflector will be the same. So here from point A, you shot towards point B and D. From point B, you shot towards point A and C, and so on along the figure. Now, what about these columns? I already mentioned that here we have a calculated horizontal distance and a calculated vertical distance. However, some instruments, on the basis of this information during the measurement, will give you the horizontal distance and the vertical distance. Again, what are these? Let's take a look at them. If you set up the instrument at one point and you shoot towards the prism, you will have the slope distance and the vertical angle. On the basis of the vertical angle, you can calculate the horizontal distance and the vertical distance simply by applying the cosine and the sine of this vertical angle. This vertical angle can be positive or can be negative. And that is what you enter in your table. And you get the horizontal distance and a vertical distance for every distance measured. Now that you have the horizontal circle reading at point A while shooting to point B and point D, you can calculate the angle in between. In other words, you can look at this figure and calculate this angle from this foresight and this backside, from this foresight and this backside, from this foresight and this backside. Each time you can calculate an internal angle for this figure at each point. Now, these angles may be affected by small errors. What to do about them? Well, what you do is first you add up these four angles, in this case 4, and you apply this equation. This equation here, 180 times n minus 2, gives you the total sum that these angles should add up to. So here you have 4 vertices in the figure, therefore n equals 4, and this becomes 2. 180 times 2 is 360. So all the angles inside this figure of 4 corners should add up to 360 degrees. This formula works even if you have 10 corners. Then it would be 10 minus 2 is 8. 8 times 180 will give you the total sum of those angles. Now, how do we correct those small errors in the angles? First of all, we calculate our misclosure. So our sum in this case should be 360. It isn't. It actually is slightly above that. So what we do is we simply divide the difference between this number and this number, which happens to be 0.0012, as shown here. We divide by the number of vertices, and we apply this correction to each angle. And we have a table portion for that. It's a new piece of a table. It's shown here. Here we have all our raw angles. They add up more than 360. They should add up 360. So the difference between the two is our misclosure. We change the misclosure, the sign of the misclosure to come to a general correction, and then the specific correction for each angle is the correction divided by 4, which is the number of vertices. So we apply this to each one of these, and we get our adjusted angles. And if we sum up the adjusted angles, we get a total of 360 degrees with no misclosure. And that's a good check. It means that we have then done our adjustment of the angles correctly. So now that we have the corrected angles for our corner, for our inside angles at each corner, we can calculate the azimuths. Now, the azimuth is something tricky, but it is the following. If you take the azimuth of AB, which means it's the azimuth from A to B, then this is the direction in space it takes in a horizontal plane. So if we want to calculate this azimuth, what we do is we take this azimuth plus 180 degrees and minus this angle. I repeat, you take this azimuth plus 180 degrees minus this angle. There's another way of doing it, of course. You take this azimuth, you subtract 180, and you subtract this angle. So there's two ways of doing it. And here you have one of those ways shown in an equation. This is calculating the azimuth BC. Now the azimuth CD, which is this direction here, is calculated from this azimuth. So this azimuth is equal to this azimuth plus 180 minus this angle. The azimuth of this line equals the azimuth of this line plus 180 minus this angle. Now, finally, we take this azimuth equals to this azimuth plus 180 minus this angle. you should get this, and this is what we're doing. We started with this azimuth here, and we end up with this azimuth here for the same line. This is our check. It means that we've done our angle adjustment correctly. So now, angle-wise, our traverse closes. Now we can do this work in our table. So here we have another portion of the table. It starts off by telling us that these are the coordinates of our point A, our starting point. This is our starting azimuth. This is the angle between the point P and the point B. That's the angle we calculated initially. And so now we have an azimuth for the line AB. These are the four adjusted angles for our points A, B, C, and D. And now these are our azimuths calculated for our lines, the four lines of our traverse. In addition to that, we have taken the distances from our first table, our horizontal distances, and placed them in here. These are just copied from the previous table. And these angles are copied from the previous table. So here we have used this table to calculate the azimuths by following the same procedure of adding or subtracting 180 and then adding or subtracting a corner angle. So now we have dealt with angles and azimuths, and we are complete in that respect. Now what we need to do is see how we adjust distances. We adjust distances indirectly, not by adjusting distances, but by adjusting components, x and y components of distances. This x component is called a departure. This y component is called a latitude. And they are calculated from this horizontal distances and from the azimuths. These are calculated from the adjusted angles. So how are these things calculated? Well, simply, we have to keep in mind that the azimuths are this at this angle here is the azimuth of line AB. From north, this angle here. And from line AB, actually, we go further. We have to extend this line this way, and then from north, it's all the way around to this line. That's why it's 345 degrees. Since we're dealing not with this angle here, but with this angle here for the azimuth, for the purposes of using the azimuth, this departure here will be equal to this distance times the sine of this angle. And this latitude will be equal to this horizontal distance here times the cosine of this angle here. The fact that you're using azimuths will switch your trigonometry. Sines become cosines and cosines become sines. Be very careful with that. And this is reflected in our table. So here we have used this horizontal distance and this azimuth to calculate our departure and our latitude. And we've done that for our line AB. And we have repeated that for our lines BC, CD, and DA to come back to A. Then we add up our horizontal distances. This is the total length of our traverse. Now, this is an important number, as we will see in a moment. Now, here we make sure that our azimuths close, which it does. We did that previously without the use of the table. Now we do this in the table. Once we have calculated our departures, or the sum of our departures should add up to 0. That means that we should be back at point A. If we're not back at point A, then we have a misclosure in our departures. For latitude also, or the sum of our latitudes should add up to 0. If they don't, we have a misclosure. So we have to correct for that since we're not at 0. So we calculate a correction which is the misclosure with the opposite sign, the same here. We just changed the sign from here to here. And what do we have here? Here we have simply a number which is this horizontal distance divided by the sum of the distances, which gives me this value. And this value here is this horizontal distances of this leg BC divided by the total length of the traverse. So I can now take this here and multiply it by this. That gives me the correction for the first departure. And the correction for the first latitude is this times that. And I apply that to this. And I get my adjusted latitude. And I repeat that for each length. Now, if I add up my adjusted departures, I should end up getting a total sum of 0, which is correct. It's an important check. I repeat that for my latitudes, and I have a check. Now, if I want to calculate the x-coordinate of point B, I just take the x-coordinate of point A and I apply the departure. In this case, it's negative. Now, this is a very important point that I need to make here, and that is that if I take the azimuths and I calculate the sine of this value, this angle, it gives me a negative value for the sine. If I apply this negative sine value to my horizontal distance, I will get a negative departure. So it automatically, by using an azimuth as an angle, not a bearing or something else, it gives me the correct sign that I'm actually reducing my x-coordinate when going from A to B. And that is very valuable. It does the sign tracking for you automatically. That's one big advantage of using azimuths in all your calculations. It has a tremendous safety factor in it. In the case of the y-coordinate for point B, it's simply the y-coordinate of point A plus my latitude. In this case, the latitude ends up to being positive, so y increases from A to B. And I repeat that around the figure. I calculate a departure for the line BC and a latitude for line BC. For line CD, I will have this departure and this latitude. And for line DA, I will have this departure and this latitude. And these are the numbers I get, positive and negative, which is very convenient. Now I start with the coordinates of point A, which I get from up here. And to this point A, I add this departure and this latitude to get the x and y for point B. Then to calculate the coordinates of point C, I simply take these values or these coordinates of point B and I add these latitudes and departures and so on. So if I do this correctly, I should add up to get exactly the coordinates I started with, which I do. That's another important check. So this essentially completes the adjustment of this traverse in the horizontal plane. The only thing missing is the adjustment of this traverse along the elevations. And that is actually a simpler procedure than this, and it's done as follows. So at each point, let's say you have the instrument set up at point A, and this is the instrument sitting on its tripod, and so there is a height of instrument. And point A has an elevation. I want to calculate the elevation of point B, in other words, E sub B. And I have a prism standing on point B. This is the prism staff. This is the height of reflector. And from the instrument, I have a vertical angle and I have a slope distance from which I can calculate my vertical distance, which we calculated previously in one of the tables. Remember, we calculated the horizontal distance and the vertical distance. That's what I'm talking about. So the elevation of point B then equals the elevation of point A plus the height of instrument plus the vertical distance minus the height of reflector. And that's the equation that is shown here. So you repeat this calculation from A to B, do it also from B to C, from C to D, and then from D back to A. So when you come back to A and you end up with a slightly different elevation, then you have an elevation misclosure. And so how do you correct for that misclosure? If this misclosure is acceptable, then you don't have to redo the traverse, remeasure the traverse. So if it is acceptable, all you do is you take this misclosure, divide it by the number of corners, and for each corner, you correct the vertical distance by that portion of that misclosure. So in other words, you distribute your misclosure among your vertical distances. Since you have one per point, you apply that at each point, and then you recalculate the elevations, repeating the process I mentioned before, going from one point to the next point, and so on. You should then have a misclosure of 0, which would complete then the adjustment of the traverse. I don't show a portion of the table to do that, but this is a very simple procedure. If you end up with a 0 misclosure at the end, then you have done it correctly. But remember, you have to apply the same portion of your misclosure to all the vertical distances, the same little number. All right. I hope you have enjoyed this session, and we'll see if we have some more sessions coming. Stay tuned. Thank you very much.